Thanks for coming today. I am going to be talking about MVCC. It's a very common database concept. This talk is designed basically for people who are trying to understand how databases achieve high concurrency. My name is Bruce Momjian. I'm one of the Postgres core developers. Work for EnterpriseDB, speak at a lot of conferences. This presentation has actually been given several times around the world. Most recently, yesterday, we had a Postgres day here at OSCon, and I was able to give this presentation in its normal time slot of 90 minutes. Because I have 40 and I have 89 slides, you can expect that we will be brief in certain sections of this slide deck. If you'd like to see the full presentation, all of my presentations are at that URL. There are over 30 PDFs there, all Creatively Commons licensed, that allow you to basically view and learn from. EnterpriseDB actually has some recordings of many of my presentations as webcasts, so you can go there if you want to actually hear the audio of the presentation. So let's get started. I have some sort of preview material I'm going to have to skip in the interest of time. So the big question is, why MVCC? Why is it important to understand the internals of database systems? Why is it important to understand how they achieve the high concurrency that they often achieve? The answer is there's probably three major reasons. MVCC, or Multiversion Concurrency Control, which is the sort of big most word that we carry around, does affect query behavior. So if you understand it, you can better predict how queries will behave. There are also performance impact and some storage impact in what MVCC does. Again, if you don't understand what MVCC does, that's fine, because we're going to explain it to you. I'm just trying to tell you why you might want to know exactly how it works. So what we're going to talk about today, I'm going to introduce you to MVCC, go over some concepts. Again, I'm going to encourage you to ask questions. This is a very complicated topic. You usually want to give this talk and get a lot of sort of strange looks from people, sort of like, how can that possibly work, or how does it work if X happens? Again, I'll be glad to sort of flesh out some of those for you in the time that we have available. Then we'll talk about implementation details. I'll show you some examples of queries that actually show you MVCC working inside. And finally, based on the amount of time we have left over, we'll talk about some of the cleanup requirements that we have. So any questions before we get started? No. Okay. What is MVCC? MVCC is the method that Postgres uses to allow high concurrency. The real takeaway, what most people think of when you think of MVCC is this last phrase right here. Readers never block writers, and writers never block readers. Sounds like an impossibility. For those of you who worked with databases in the 90s like I did, where you used to have to do dirty reads so reports could finish. You'd have out of locks errors when you did big updates. If that's familiar to anybody here, that is the pre-MVCC database world that I certainly grew up in. Fortunately, that has changed. MVCC as a concept was actually developed in the 70s, but only became popular in the late 90s, and obviously very popular as a Postgres implementation. Many of these slides have a lot of words on them. I'm not going to read the words. The words are there, so if you want to go back later and read this presentation again because you're sort of less confused, feel free to do that. That's why I've actually made a fairly text-heavy presentation, because I think it often needs more than one reading or more than one preview to really sink in exactly what this thing is. Who supports MVCC, or what other databases support MVCC is the proper title for this. Oracle has supported for many years. DB2 has a partial implementation. Somebody actually explained what that partial means one time to me. NDB and MySQL uses it. Informix uses it. Firebird uses it. Microsoft SQL optionally uses it. But it's disabled by default. So it is a very popular technology in most commercial databases and relational databases. So what is it? This is the slide. This is the slide that really sort of keynotes everything that's going to follow. If you understand this slide, I think the rest of the slides kind of follow. So I'm going to go through it fairly slowly, and then we're going to kind of zoom after this. So basically what I'm showing you are the three sort of big operations that you normally do with databases, aside from select. So these are your, your typical data modification commands: insert, delete, and update. And the first thing you might realize is, well, how come we do it in that order? Like, why isn't it insert, update, delete, which is the way most people say it? And the key is really this last entry here. You'll notice that update is really a combination of a delete and an insert. And that's going to be key, I think, when we start to understand how MVCC works. So let's start at the top. Let's start at insert. So insert's fairly simple. You're adding a row, right? But what's different about it, you're going to notice, is that there's two fields on the row that are not normally visible. You don't normally see them, but they're there. Okay. The first field is called create. Okay, it's the field that creates the row, and that 40 that indicates the transaction number that created that row. So in this case, I know that that row was created by transaction 40. Now you might think, well, why do I care about that? Well, I'm going to show you later that information is actually pretty important. Okay? The second field is called expire. The expire field is not used in this case. You just insert it. But in the second example, we actually do use the expire. This is a delete. It's actually the same row as this one. You can see the same 40 is actually up here. But what the delete did was to put a transaction ID on the expire column. And that indicates that that row was created by transaction 40, but deleted by transaction 47. Okay? Again, why is that important? Doesn't seem important. You're going to see it is. Any questions so far? Okay. Last one, update. Update is a combination of a delete of the old row and an insert of the new row. That's really where the word multi-version concurrency control comes in. You've heard, it's 4 words, multi-version. In the old database systems that I used years ago, there was only one version of a row. Okay? If you updated a row, it overwrote the current row. Okay? There was one copy. You basically wrote over top of that row every time you did an update. What's different about MVCC is instead of overwriting that row, we create a new row. And what we do is we expire the old row, like a delete, by putting our transaction ID on this row. And then we insert or create a new row by putting our transaction ID on the create field. Okay? It's not a coincidence that 78 is used in the expire and also in the creation of the next row. It has to be that way. Okay? Because that operation is atomic. We've deleted one row, we've created a new row at the same time. Okay? Any questions so far? Okay. So, how does this all kind of come together? Again, I've been showing these fields, and they're sort of like, well, big deal, why are they important, what use are they? The real answer is snapshots. Okay? With MVCC, there is this sort of concept that I know sounds almost postmodern. Like when we think of a database, either a row's there or it's not there, right? Either the row says 7 or the row says 12. You can't say both, right? But in MVCC, you have this sort of relativistic approach to data. So that effectively, your snapshot determines what data that you see. And it sounds like it shouldn't work, just like open source shouldn't work, but it does. And I'm going to actually show you a lot of examples in this presentation exactly how it works. Okay. So let's look at a concrete example. Okay. In this concrete example, I'm going to use a snapshot that I outline on the left-hand side. And those rules that I define on the left-hand side really define which rows on the right-hand side, the snapshot on the right-hand side really tell me what rows are visible on the left-hand side. Okay? So it's really my snapshot that determines what I see in the database. And some other session connected to that database may have a different view of the database than I do because it has a different snapshot. And that really kind of has to sink in, that we assume that two people running queries at different times should all see the same data, but that's not often true. Okay? You basically have different people who are getting snapshots at different times times, in the timeline, depending on the time in which your snapshot's taken, they're going to see the database in a different way. What's also absolutely required is that once you take a snapshot, your snapshot will never change. So no matter what happens in the database while you're doing your select or your update or whatever, your view of the database is not going to change. Why is that important? Well, as I said a little earlier, databases that did not have MVCC often had great trouble running concurrent operations, running batch updates, running big reports. Because a report would try and run, it would try and see how much money is in the bank. And at the same time it was running, all these transactions were adding money, moving it around, moving $1,000 from one account to another, and that report often yielded like sort of approximate results, right? Because you had to use things like dirty read and sort of fake your ability to see what's happening in the database. Okay. Or you'd have to run at night when you knew nobody was going to be in the system. That's really how we had to do it in many ways, right? I used to work for law firms, we'd run financial reports and make sure everyone was out of the system when we ran our reports because we didn't want any kind of any other changes going on. Okay? Well, with MVCC, that's not a problem because once you get a snapshot, that snapshot guarantees that you will see a consistent copy of the database for the entire life of your statement, even without blocking any concurrent operations that are going on. Again, readers don't block writers, writers don't block readers. So how does that work? And let me ask this first question. Yes?
Is the highest number committed transaction, is that always the newest time-ordered one?
Okay, so let's actually look at the snapshot and that'll answer your question. So let's look at the snapshot. So the snapshot we have here is that we know that the command counter at this point, the highest committed transaction is 100. Is that always going to be the highest current one? No. Okay. It actually is only important because that's my high watermark in how I have to look at my open transactions. Okay. So if my and I'm very much trivializing this example, okay? But basically the way the snapshot works is I find out what the last committed transaction was, or the highest number committed transaction was. And then I record all of the running transactions that are lower than that highest number, okay? And so effectively I have a high water mark, and then I have all these numbers beneath me that are still running. Effectively, to answer your question, some of those numbers could be higher than 100, which is what you're actually asking. You're saying, is that really the highest transaction that's a growing process? No, it isn't. Okay, it's kind of my high water mark that I have to track. So anything above that, I know nothing is committed above that. And anything below that, I basically have to keep track of all these. Okay. So in fact, what we have is a high water mark of 100, and 25, 50, and 75 are currently running when we take our snapshot. Very quick operation, we just kind of snapshot what's going on. Okay, that snapshot doesn't change for our entire transaction. I'm sorry, for our entire statement. So let's look at these 6 rows. The first row here, we have a row that was created by transaction 30, and that row is visible. Okay, it basically means that that row is visible because it's less than 100, meaning it occurred before, it committed before I started, and it wasn't running. It wasn't one of those 3 that were running when I took my snapshot. So this insert happened before I took my snapshot, and therefore it's committed. I can see it. It's visible. Okay. Next one, different. This one was created by transaction 50. Now you might remember transaction 50 was one of those rows that was running at the time I took my snapshot. So I don't care what happened after I took my snapshot. I don't care if he committed or aborted after I took my snapshot. The fact is he wasn't done when I took my snapshot, so I can't see what he inserted. Similarly, this one is a new row. It was inserted after I took my snapshot, 110. Again, this is not a row I can see. So you can start to see how you have this sort of visibility where you can see certain things and not see certain things. Okay, it's really kind of freaky, but it's really the only way to really understand how the system works. Looking down here, we have a row that was created by a valid transaction and expired by a valid transaction. So it's deleted. We can't see it. It's still in the database, we just can't see it. Other people might see it, other sessions might see it, depending on their snapshot, but they cannot see that row. The next one, this one is visible. The reason that's visible is because it was expired by one of those running transactions, right? So I don't see the delete, it's still valid to me. Might be invalid to somebody else. Same thing here. It was deleted after I took my snapshot. So okay, we can see it. When you start to see, every session has these same rules that they go through. It allows everyone to kind of keep working without kind of stumbling upon each other and guaranteeing that we're getting consistent results during the entire session that they're running. Yes?
So what happens if you're seeing a snapshot 100 in front of you, and you take one of those two bottom ones which are visible but which have already been updated by someone else but not committed? If you make a change to try and commit that, it appears to be you're then updated, you're trying to update it, but it's already been updated by somebody else,
right.
And you're not updating it, you're not seeing the latest.
Right, what will happen in this case if I tried to delete this row, for example, okay, I would actually go to sleep and I would wait for 75 to finish. If 75 finished, then I would delete the row. If 75 aborted, I'm sorry. If 75 committed, then I don't see the row, right? Because effectively, I didn't see it, right? It happened, it's gone now. If 75 aborted, then I can see the row, and then effectively I can do it. So the rule was that readers can't block writers, and writers can't block readers. What we didn't say is that writers can block other writers. And effectively, that person's doing a delete, I'm doing a delete, we're going to block.
So one of you will send a message saying this was updated by is a refresh.
What will actually happen is that the query will stop and wait for that to commit or abort and then move forward. So you won't actually get a message of the client unless you put a timeout in there or something.
I'm not sure I understand, because if someone updates a row, then I want to do another update.
Oh, okay, so we're doing 2 updates, okay.
If we're doing 2 updates, then there's one update. I always thought it was a good rule when the person who was doing an update should see the latest version before he can.
That's what will happen. So basically, if that's an update in that case, I'm going to see the new copy of the row. I'm going to sleep waiting for that transaction to complete. Once it completes, I will reread that row with the new data and then move forward.
So you can see the new data.
I would actually see the new data. And if there's a where clause in the query, I will retest the where clause on the new version of the row because it may not match anymore the copy that I have. Very good point. So, confused yet, right? Very complicated stuff. This is a quote by one of the Berkeley guys basically saying, this stuff's really hard, and if you think it's wrong, think about it. I know that. So, this is really confusing. Let's take a look at implementation issues. Here I actually have a little setup I did. And here's an example of a query using Postgres, unmodified, where I basically created a temporary table. I've inserted a row, and now I'm actually looking at the creation and expire fields internally in the database. Now they aren't called CRE and EXP. They're actually called XMIN and XMAX. That's just what we got from Berkeley. Okay? So XMIN is the invisible creation field. XMAX is the invisible deletion field. And as you can see, in this case, I've done an insert, and you can see that's actually the transaction ID that did the insert. It is exactly the same as this. Right? In fact, I even have the SQL that I'm using for this. This whole presentation is in that SQL file. So if you just run it, you can actually prove that I'm not making this up. Let's look at delete. Here we insert a row. We take a look. This is our insert right here. Okay, and no expire. Then I begin a multi-statement transaction. I delete the row, and then I look out here in another session. I start a separate session. So I have a new visibility, a new snapshot. And a new snapshot, I can't see the row in my current transaction because it's not in my snapshot. But I can see it if I start a new session because this hasn't committed yet. And if that doesn't make sense, I'm sorry. Okay? It gets only worse, right? So here we actually have a case where I can see the deletion, but I can still see the row because I'm in another session and the session hasn't completed. So it's one of those running transaction numbers that I can skip, okay? And you can actually prove it right here. This is in this outer transaction number. I can actually, there's the number. So that is my delete right there, okay? What about an update? I'm sorry, it's this case right here. This is it right here. So that is that. Update, exactly the same. Put a row in. Here's my insert. I update the row from 1 to 2. Here's the 2, here's the 1. It's this, okay? So this, and this is that. Okay. What if I abort a transaction? Here I've actually insert a row, begin a multi-statement transaction, delete the row, and roll back. So you're like, well, what happened? Right? Do I have to clean up the delete? No. If you do a select, you can actually see the row, and it has a delete on it, doesn't it? But we actually have a separate table called PGC log that tells us which transaction number is aborted and which transaction number is committed. Right here. The bit pattern tells us that this row aborted, so I can still see that row because when I go to look it up, I actually look that number up in this table, and when it says it's aborted, I know I can ignore it. This allows us to do, you can delete 10,000 rows and abort it. Postgres is done immediately. Because it doesn't have to go back to those 10,000 rows to do any cleanup. It just has to mark that transaction is deleted and the job's done. Yeah?
Why even bother writing the Xmax in the first place then for the transaction?
We didn't know at this point we were going to abort the transaction.
Wouldn't it be more efficient to go back and actually clean those up and unwrite those?
No, because you get into the problem where you could effectively, if you're deleting, you get into the, out of locks, out of row locks, out of memory. There's all these kind of constraints. You could have modified 20 tables and 10 rows in each table during that abort, right? And that would then mean that we have all this stuff that has to happen on an abort. Effectively, right now, we just abort, we just set the bit, and we just walk away. And when we start to talk about cleanup, you're going to see that there's a sense that the cleanup is inefficient in this case, but when we get to cleanup, you'll see that there's a whole infrastructure for cleanup that ends up working just as well. So it's not something we ever want to do. Okay. We actually use Xmax for row locks also. If you do a for update, you can actually see the row lock there, but there's a special flag that tells it's a row lock and not a real delete. Okay. Multi-statement transactions, I'm not going to go into this. Effectively, there is a third field called CMIN or CMAX, which is used to track multi-statement transactions. Not really significant here. This slide is interesting because it actually shows you 4 rows from 2 different transactions. So I have 1 row in red from an outer transaction, and I have 3 rows in purple from an inner transaction. And effectively, you can see here from a select that you have here's the 1 row from the first one, and here's the other row. So my point is just to show you that you can mix different rows from different transactions in the same table, no problem. Even when I do an update, now I've updated all of them, and you can see the visibility only shows me the first row, because again, I'm in another session, my snapshot can't see the inserts that happen in the transaction log. I realize I'm throwing a huge amount of information at you. Again, that's why I gave you the URL, because you might want to go back and look at this again, and even run the SQL yourself and see what you're doing. Common command ID, I'm not going to go into that either. Basically, common command ID is used when you have an insert and a delete or an update in a multi-statement transaction. Not tremendously important. So, in summary, Xmin, when we created Xmax, when we read Slide, those are the 2 things. And again, understanding those rules is pretty important. So any questions before we start cleanup? Yes?
Since so much seems to depend on transaction values being monotonically increasing, do you have to worry about overflows?
No, we do not. We actually can wrap around the counter, the transaction counter. It's 4 bytes long. So we basically have a process as part of the cleanup that will kind of go around every billion transactions. And it sets all the committed transactions to a fixed number of 1. And therefore, when it wraps around to 0, it wraps around actually to 2, to 3. When it wraps around to 3, we don't have we know that there are no transaction numbers being used for the next 2 billion that are currently stored in tables. And it's all wrapped up really in the whole cleanup process that I said it's pretty involved. Ideally, we wouldn't have any cleanup, but we've actually done a really good job, and I think you're going to see some pretty elegant solutions here for this. What questions?
Can you give the URL again?
I'm sorry?
Can you give the URL again?
Of course, it is here. Right there.
Okay.
If you barely spell Momjian in Google, it will find you. Okay? Yeah, I've tried a whole bunch of misspellings, and it always finds it. So, you could probably just type Bruce in Postgres, it would find it. Okay, so let's talk about cleanup. Oh, I'm sorry, other questions?
I have a question on the last slide there.
Yeah.
I think you're saying that these numbers that we're looking at these are transaction numbers.
That's correct.
And if we start a transaction, then it pulls a number from this sequence data. And then if we roll back without committing, that number has still been used.
That's correct.
And you get the symbol in that column. So what triggers pulling the next number off this? Because I can understand that you might pull a number off when you were commit, but it doesn't work that way.
No, you pull a number off the first time you modify the database. So select doesn't get a number. So as soon as you issue an insert update for leave, we'll give you a number, and you'll use that number for any transaction.
I'm used to typing the words SQL prompt.
Yeah.
But nothing happens until I guess it's when you run that insert save.
Yeah, when you run an insert statement, it gets the server. It isn't happening as you type it, it's happening as we see. So let's take a look at cleanup. MVCC cleanup is kind of a pain, but we still need to do cleanup. Even if we didn't have MVCC, we would still have to clean up deleted rows, and we still have to clean up aborted transactions. Okay? MVCC adds some additional cleanup requirements. Update now has 2 copies of the row, so we need to clean up there. And finally, we also have the issue of we can't clean up stuff as aggressively as we want. We have to do it in somewhat of a delayed manner. Because there might be snapshots out there that want to see the old data. Okay? So people might want to see the old data, and therefore we can't clean it up as quickly. We have to make sure that nobody can see it before we delete it, before we remove it. Okay. So let's take a look at what Postgres has. 2 methods of cleanup. One is an on-demand cleanup that can happen per page, and 2, we have a bulk cleanup by something called auto vacuum or vacuum. I'm going to show you examples of each of these. What things can be cleaned up? 3 things: the data, the item pointer, which is also on the same page as the data, and the index entries. And you're going to see different phases to clean up different parts of the query. That's what a heap page looks like in Postgres. They're all in K. They have some item pointers at the front, and there's some data at the back. Okay? Expanding that out a little farther, we have indexes, which also require storage, and those indexes actually point to item pointers. Okay? And the item pointers themselves point to the data. Okay? So it's like a double indirection. Index points to the item pointer points to the data. We're going to exploit that quite a bit when we start to talk about that indirection, when we start to talk about cleanup. So, first thing. Let's take a look at this example. We've got 3 rows. Let's suppose rows 1 and 2 aren't visible to anybody. They're dead. So what we can do is we can actually remove rows 1 and 2. See, they were here. Right? We can remove them. We can move 3 down to the end. And we can just mark the item pointers as dead. Why can we do that? Because the indexes point to the item pointers. The indexes, basically, if we just tell it there's nothing here, the indexes know there's no data, and we just say there's nothing there. Okay, so that's one cleanup we can do very, very easily. Another cleanup we can do by running vacuum. Vacuum, again, is a bulk operation. It's going to clean out the indexes. Once it cleans out the indexes, you can see nothing points to 1 and 2, and we can now clean up those item pointers.
The horizontal tool where I was showing the direction that rows.
Yes. So effectively, item pointers would go from the beginning of the table forward, and the data goes from the back of the table toward the front. When the two meet, you're out of space on that page, you create a new page. Good point. So you can see sometimes we're marking them dead, sometimes we're marking them unused. So let's go through some specific examples. Single page cleanup won't happen unless the page is kind of full. So I'm going to basically fill it with 240 rows of nothing, zeros, and I've actually achieved a 6% full, 6% empty. So I'm 94% full at this point. I'm pretty packed. Okay. So now I'm going to insert a row. I'm going to actually look at the row using my special view that I defined much earlier. You can see that that is marked as normal. And it's in slot 241, so it's the 241st item point. Okay? If I delete the row and add row 2, what happens is I actually have, here's my 2 rows. This is my original row, 241. This is my new row, 242. So where's the cleanup? Well, we issue a delete again, and we now insert a 3. So we have 1, 2, 3 now. But when I go to look at the table, effectively 241 is now marked as dead. That's because the system knew nobody could see the 1, and therefore it just got rid of the data, kept the item pointer, and got rid of the data. Okay? I'm going to do a select, and what do you know? The second one's going there. So what you're basically seeing is an example of this. For the 2 item pointers, because they're pointing to data that nobody can see anymore, the system, even from a select, just by looking at the row, it goes away in terms of data storage. Item pointer's still there, index pointers might be still there, data's gone. That's why it's marked as dead. If I issue vacuum, which again is our bulk operation, you can actually see they've been marked out to unused, which matches exactly what this is. Because the index pointers are gone, and we can now mark those item pointers. So you can see the system's pretty aggressive about kind of cleaning stuff out. Could be ignored rows, could be deleted rows, could be old updates. This feature was added in Postgres 8.3, actually developed by an EnterpriseDB employee, obviously with the direction of the community. In fact, the whole spec kind of came from the community. He kind of took it. His name was Pavan. He's an amazing guy. Quiet guy. You wouldn't think he was like a genius, but he obviously is the way he did it. And then he took our ideas and even made it better, which is tremendous. Exciting how we get different ideas from people. And Postgres is, I'm always learning something from these people because they're just so smart. Another thing Postgres does is it has a free space map. That helps to tell the system where which pages are have empty space. Vacuum handles that quite easily. Here's an example where we actually put a row in a table and look at the free space. You can see every time we insert it goes down, and every time we delete, and then when vacuum it goes back up again. So sort of a way of telling the system where the free space is on the system. If we have some empty data at the end of the page, if you have like 3 pages at the end of the table that are empty, and you run vacuum, Postgres will automatically shrink the table to get rid of those 2 pages, to return to the operating system. One case you might be wondering about is the update case. The update case is pretty tricky because although we have inserts and deletes, updates happen a lot. Okay? Probably the hardest one is where you got a counter that goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all the time, right? So you have one row that's just churning all the time. And fortunately, again, thanks to Ravon, we have some really cool feature here. Here's a case where you have one row, version 1, basically we're starting out with one row, we update it. So then we have version 2. But what's interesting about the way the system does this is that instead of creating a new index entry, we just have this item point to version 1, and then version 1 points to version 2. So we didn't have to create an extra index entry for this update, because actually the rows share the same keys. So we could just have the chain on the page represented by this one item. Yeah. This is all on the same page. This only works if the 2 rows are on the same page. And we've already loaded the 8K page, so it's like, you're right. If we go to a different page, this will not work. And in fact, one of the reasons we're aggressive about cleaning up a page is if somebody tries to update and we don't have room on the page, we'll try to get rid of stuff so we can get it in there. You're absolutely right. What's really bizarre is when we get to version 3. So we have version 1, version 2. When we get to version 3, all of a sudden, version 1 goes away. And instead of having the item pointer like stay, it now points to the second one, because we don't have a chain anymore from 1 to 2. Right? So item 1 just points directly to item 2 without a row at all. These are actually called heap-only tuples, or high. Okay? What's really interesting is that this can continue forever. I'm bouncing back between version 2, version 3, and version 3, version 4. As you can see, this pointer just kind of bounces back. Single index entry, and these redirect now kind of oscillates between the 2 versions. Now we might have a chain of 3 or 4 versions in this case, but the same process occurs as much as Postgres can clean up the rows if we like. Okay? Once the actual chain is gone and version 3 can't be seen anymore, we can get rid of all the other versions, and we can just point the pointer right here and right there, and we're done. So as you can see, this really reduces the problem of having too many index entries for an update, and also the problem of having what we call consuming item pointers. So you're consuming a lot of item pointers to the update. Let's look at a quick example here. Here's an example. Basically, 1 row on the page. I do an update. Here's the normal row. Okay. I do an update again, and you can see the redirect happen. Exactly what we're talking about right here. Okay. If I then do an update again, it redirects now 1 points to 3. Exactly what this slide shows. And then finally, if we do a select, clean it up, we only have this one. And you can see this one's now marked as updates. So you can see we've even optimized the update case, so it really works very efficiently. Vacuum doesn't remove the redirect, we just kind of leave it there. It's not that big a deal. Couple other, I'm not sure what else I really want to show you. This one issue, though, I have to talk about. We can't do this tricky update if you change an indexed field as part of the update. Because remember, that whole chain has to share the same index pointers. So if you change an index column, we can't do this change. And we have to do the old version. And here's an actually as an example, I got 3 dead item pointers from 3 updates. Remember, I could recycle the data, no problem, but I couldn't recycle the item pointers because I have indexes pointing to those, because you modify the update to the index. That's a summary. Effectively, 2 types of cleanup. Single page, that's what you can do. Vacuum, that's what you can do. We end with this slide. I think it's appropriate for MVCC. Effectively, there is no up and down, valid, invalid. It all depends on what your perspective is. That is an extra thing called L3. Thank you very much. I'll be up here to answer any questions. I am out of time. I hope you have a great time at OSCon. I'm certainly looking forward to it very much too. Thanks very much.